Welcome back to the second Programming and Simulation lecture. This week I will talk about differential drive, odometry, and infrared sensors. In fact, this week's programming assignment is focused on implementing the robot's sensors and actuators. Therefore, you will need to transform from the unicycle dynamics in the controllers to the differential drive dynamics in the mobile robot. You also need to use the wheel encoders to keep track of the robot's position and orientation. This is called odometry. And third, you will need to use the infrared sensors to measure distance to any obstacles that might be around the robot. The simulator emulates the QuickBot, and the QuickBot is defined in the quickbot.m file. This is a class, and it's located in the robot package. Packages in MATLAB are denoted by a plus in front of the folder name. This robot has a two-wheel differential drive, meaning that each wheel is independently controlled by a single motor. And it also has a wheel encoder for each one of the wheels. And these wheel encoders are responsible for measuring the distance that each wheel travels. And they have a resolution of 32 ticks per revolution. And the robot also has 5 infrared sensors. And these infrared sensors can detect any obstacles that are within a range of 4 to 30 centimeters in their field of view. Following is a little diagram to explain to you how the simulation actually works. First of all, there is the simulator, and it has a timer object. And this timer object calls at every time step the execute function inside the supervisor. The supervisor is really the decision maker, and it's responsible for, first of all, gathering the sensor information from the robot. It then selects a controller and passes the sensor information along with an estimate of the robot's position and orientation to the execute function in the controller. This execute function in the controller then computes the appropriate linear and angular velocity of the robot, which is then converted to the left and right wheel speeds of the robot and passed back to the robot. The supervisor is also responsible for updating the estimate of the robot's position and orientation, and this whole process is repeated at every time step. The supervisor itself is defined in the qbsupervisor.m file, whereas all of the controllers are found in the controller package. The first part of this assignment is to convert the linear and angular velocity in the controllers to the left and right angular wheel velocities on the mobile robot. You will do this in the unit-to-diff function, which is defined in the differential drive.m file. This function takes in the linear and angular velocity of the robot and returns the left and right wheel speeds. This skeleton code shows you how to retrieve the radius of the wheel r and the distance between the two wheels l, which you will need to use to calculate the left and right wheel speeds. The second part of this assignment is odometry. What you need to do is to measure the distance traveled by each wheel and estimate the position and orientation of the robot using those measured distances. You will implement this in the update odometry function, which is inside the qbsupervisor.m file. Let's take a look at the skeleton code for this function. Here you have the skeleton code for this function. First, you will retrieve the wheel encoder ticks from the robot. Then, you will recall the previous wheel encoder ticks, which is achieved by retrieving the previous ticks stored in the previous iteration of the code. Then you will retrieve the current state estimate, meaning what is the current estimated position and orientation of the robot. Then you will retrieve the useful constants such as the radius of the wheel, the distance between the wheels, and how many meters are there for each tick of the encoder. Then your part comes, which is to implement odometry by computing the difference in the x position, the difference in the y position, and the difference in the orientation between now and the last time odometry was updated. You will then add these deltas to the current estimate of the orientation and position, and save that as the new estimate. You will also need to save the current number of ticks in the right and left wheels for the next iteration. The last part of this assignment is to make sense of the IR distance sensors. In particular, these sensors will return voltages in the range from 0.4 to 2.75, and those correspond to distances between 4 and 30 centimeters. The relationship between distance and voltage is shown in the graph on the left. What to make matters a little bit more complicated is that the robot actually returns an integer value in the range of 200 and 1,375. But these values simply correspond to the voltage divided by 2 and then multiplied by 1,000. Since the graph in the previous slide is not linear, we need to use the MATLAB's polyfit function to find a fifth-order polynomial that will fit the data. We will then use the coefficients from that function and the polyval function to convert from the integers to an actual distance in meters. You will do this in the getIRDistances function. This function is defined in QuickBot.m, and you need to implement two specific parts. The first, you need to properly convert from the integers to the voltage, and then you need to hard-code the coefficients that were output by the polyfit function. To help you test the assignment, we've included a GoToAngle controller. This is a P-regulator which will simply steer the robot to a specified angle. If you wish to change the angle to which this robot steers, you need to go into the constructor in QBSupervisor.m and change this variable right here, object.theta_d. I have it set to pi divided by 4, so we expect that the robot would drive off at a 45-degree angle with respect to the x-axis. Let's see this in action. I'm going to hit play, and what we should see is the robot drive at a 45-degree angle. I'm going to move the graph out of the way, and we're going to follow this robot. And as you can see, it's driving at 45 degrees with respect to the x-axis. It's going to just continue driving at this angle all the way until it's going to crash into this red wall. There we go. We've had a crash. You'll see in the command window that I've actually been spitting out the estimated post from the odometry at every time step. And you can see that the values that I'm getting for the angle are close to pi divided by 4. So this controller successfully steers the robot towards that angle. My two tips for this week are, first of all, to make sure you read the section on week 2 in the manual for more details than you find in these slides. And also, to use the commented out fprintf statements that I've included in the comments in the code, and to maybe add some more of your own. And this is really useful for debugging because, for example, when you're dealing with implementing the odometry, you want to print out what you're currently estimating the position of the robot to be. You know, for example, you can easily see that my robot drove at 45 degrees, but I also needed to print that out to the command line to make sure that those values match up. And that's it for this week.